Hello, this is the BirdNest project, presented to you by Claude, Eric, and Mike. The goal of this project is to find the bird nest efficiently, in order to help ecologists to spend less time finding the bird nest and more time studying and helping the birds. As we know, bird nests are quite hidden to protect the young birds from predators, so it is very difficult to find them directly. What we want to do is to exclude the areas where it is impossible to have bird nests, and to identify the area with high potential, so that the ecologists only need to pay attention to the areas where bird nests are more likely to be found. We want to use a computer vision approach to identify the high priority areas. So we need images. We'll have access to many images generated by different cameras mounted on a quadcopter, which can scan the landscape quickly. We have near IR images, which can detect the plants. We have thermal images, which can detect heat difference in the environment. And we have visible light images, which has the highest resolution. So far, we processed the near-infrared images and the visible light images. Now let's take a look at what we did with each type of images. The image on the left is an image that has its red value in the RGB replaced by near-infrared. And based on that value, we can calculate the normalized differential vegetation index, NDVI, which measures how healthy plants are. With the NDVI, we can tell what material are living and what are dead. So, if you look at the image on the right, which we did a threshold on the NDVI, and found what material are living and what is dead. Of course, in a bird's habitat, half of the material, such as grass and trees, will show up as positive, indicated by the white pixel on the picture. And the other half, materials such as rocks, soil, and water, will show up as negative. Intuitively, visible light images give us the least information on bird nests, because bird nests are hidden from view. However, we can find the trees where birds build their nests. Since visible light images have the highest resolution among all the different images we have, we decided to do classification on visible light images. In a nutshell, classification takes an image and identifies which part of the image belongs to which of the classes. The algorithm should magically label leaves in the image as leaves, grass as grass, and so on and so forth. Based on our current progress, we can exclude up to 89% of the area by classifying. Now we'll explain to you how the magic works.
Finally, I will introduce how we collected the data. We collected the data manually from the field images. And like this are the grass data. And for each image, for each data image, it's 250 by 250. And these are the leaves areas. And the leaves areas are bird nest potential areas. And the soil areas, and the rock areas. Then we extract the local boundary pattern features from each data image, and then find the main features for each class. Here, for each image, we choose 3 different P and R to get 3 features, and I concatenate them together as a whole feature. Then we start to train, and the training process took 35 minutes. And then we arbitrarily choose one test image, like this image. And this image is much big, and then we divide the big image into small patches. and we do classification for each small patch. And I can show you the results here. These errors can be the bird list errors. And these errors can't be the bird list error. This error can't be the bird list error. Here I introduce the neural network method to do the classification. Neural network method is a very popular method to do the classification now. And because we don't have any access to any GPU, so we resize the original data image to 28 by 28. The image become much smaller and it will save much time to train. And we implement 4 types of layers and 3 types of activation function here. And then we wrote function for the forward process and backward process. And then we wrote the cost function to calculate the gradient and the cost. And then we wrote this program step by step by ourselves without relying any toolbox. And this program can support any architecture design. And for this project, the architecture is like this. The first layer is convolutional layer. The number of the filters is 5, and the activation function is 10H. The second layer is activation convolutional layer, and the number of the filters are 10, and the activation function is 10H. Following it is max pooling layer and fully collecting layer and the softmax layer. And we also can design the size of the filter here, and we also can design the dimension of the filter here, and then we train it. And the first cost is very large. So we update the weight and the bias again and again, and to make the cost smaller and smaller. And we can see here, and the cost become much smaller. And but actually, it took us 5 hours to train the data. And we do the test on the test images, and I can show you the results. These are the potential bird list error. There are some false positive errors there. And these errors can't be the bird list. Doing test for several images, we get the statistical analysis. Also, there are some false positives. The false negative percent is very low. It means that almost all positive errors are detected, and we can actually exclude nearly 90% errors, which can be bird list. Even though the performance for the neural network is not better than the traditional method. Personally speaking, I prefer the neural network method. It is more promising. And because for this project, we resize the original images to much smaller size image, and the data is very small, the performance is definitely influenced. If we can use the original images and we get more data, the neural network method will definitely outperform the traditional method.
In the future, we would like to process the thermal images, which can detect animals in the image using the temperature difference. After we have the 3 layers of information, near IR, visible light, and thermal images, then we can combine them to enhance our result. Finally, we want to find an efficient path for the ecologists to visit all the high priority areas. To summarize, we're doing a lot of image processing in order to reduce the search area of where bird nests can be. This will help ecologists find bird nests more efficiently so that they can spend less time trying to find the bird nest and more time studying and helping the bird.